Ocean acidification is the ongoing decrease in the pH of the Earth's oceans, caused by the uptake of carbon dioxide from the atmosphere. Seawater is slightly basic, and the process in question is a shift towards pH-neutral conditions rather than a transition to acidic conditions. Ocean alkalinity is not changed by the process, or may increase over long time periods due to carbonate dissolution. An estimated 30 to 40% of the carbon dioxide from human activity released into the atmosphere dissolves into oceans, rivers and lakes. To achieve chemical equilibrium, some of it reacts with the water to form carbonic acid. Some of these extra carbonic acid molecules react with a water molecule to give a bicarbonate ion and a hydronium ion, thus increasing ocean acidity. Between 1751 and 1994, surface ocean pH is estimated to have decreased from approximately 8.25 to 8.14, representing an increase of almost 30% in H+ ion concentration in the world's oceans. Earth system models project that within the last decade ocean acidity exceeded historical analogues, and in combination with other ocean biogeochemical changes could undermine the functioning of marine ecosystems and disrupt the provision of many goods and services associated with the ocean. Increasing acidity is thought to have a range of potentially harmful consequences for marine organisms, such as depressing metabolic rates and immune responses in some organisms, and causing coral bleaching. By increasing the presence of free hydrogen ions, each molecule of carbonic acid that forms in the oceans ultimately results in the conversion of two carbonate ions into bicarbonate ions. This net decrease in the amount of carbonate ions available makes it more difficult for marine calcifying organisms, such as coral and some plankton, to form biogenic calcium carbonate, and such structures become vulnerable to dissolution. Ongoing acidification of the oceans threatens food chains connected with the oceans. As members of the Inter-Academy Panel, 105 science academies have issued a statement on ocean acidification recommending that by 2050, global CO2 emissions be reduced by at least 50% compared to the 1990 level. While ongoing ocean acidification is anthropogenic in origin, it has occurred previously in Earth's history. The most notable example is the Paleocene-Eocene thermal maximum, which occurred approximately 56 million years ago. For reasons that are currently uncertain, massive amounts of carbon entered the ocean and atmosphere, and led to the dissolution of carbonate sediments in all ocean basins. Ocean acidification has been called the evil twin of global warming, and the other CO2 problem. Carbon cycle. The carbon cycle describes the fluxes of carbon dioxide (CO2) between the ocean's terrestrial biosphere, lithosphere, and the atmosphere. Human activities such as the combustion of fossil fuels and land use changes have led to a new flux of CO2 into the atmosphere. About 45% has remained in the atmosphere. Most of the rest has been taken up by the oceans, with some taken up by terrestrial plants. The carbon cycle involves both organic compounds such as cellulose and inorganic carbon compounds such as carbon dioxide and the carbonates. The inorganic compounds are particularly relevant when discussing ocean acidification, for it includes many forms of dissolved CO2 present in the Earth's oceans. When CO2 dissolves, it reacts with water to form a balance of ionic and non-ionic chemical species. Dissolved free carbon dioxide (CO2), carbonic acid (H2CO3), bicarbonate HCO-3, and carbonate (CO2-3). The ratio of these species depends on factors such as seawater temperature and alkalinity. These different forms of dissolved inorganic carbonate transferred from an ocean's surface to its interior by the ocean's solubility pump. The resistance of an area of ocean to absorbing atmospheric CO2 is known as the Ravel factor. Possible impacts. Increasing acidity has possibly harmful consequences, such as depressing metabolic rates in jumbo squid, depressing the immune responses of blue mussels, and coral bleaching. However, it may benefit some species, for example increasing the growth rate of the sea star Pisaster ochraceus, while shelled plankton species may flourish in altered oceans. The report is Ocean Acidification Summary for Policymakers 2013, describes research findings and possible impacts. Impacts on oceanic calcifying organisms. Although the natural absorption of CO2 by the world's oceans helps mitigate the climatic effects of anthropogenic emissions of CO2, it is believed that the resulting decrease in pH will have negative consequences, primarily for oceanic calcifying organisms. These span the food chain from autotrophs to heterotrophs and include organisms such as coccolithophores, corals, foraminifera, echinoderms, crustaceans and mollusks, is described above. Under normal conditions, calcite and aragonite are stable in surface waters since the carbonate ion is at supersaturating concentrations. However, as ocean pH falls, the concentration of carbonate ions required for saturation to occur increases, and when carbonate becomes undersaturated, structures made of calcium carbonate are vulnerable to dissolution. Therefore, even if there is no change in the rate of calcification, the rate of dissolution of calcareous material increases. Corals, coccolithophore algae, coralline algae, foraminifera, shellfish and pteropods experience reduced calcification or enhanced dissolution when exposed to elevated CO2. The Royal Society published a comprehensive overview of ocean acidification and its potential consequences in June 2005. However, some studies have found different response to ocean acidification, with coccolithophore calcification and photosynthesis both increasing under elevated atmospheric PCO2, and equal decline in primary production and calcification in response to elevated CO2, of the direction of the response varying between species. A study in 2008 examining a sediment core from the North Atlantic found that while the species composition of coccolithophorids has remained unchanged for the industrial period 1780 to 2004, the calcification of coccoliths has increased by up to 40% during the same time. A 2010 study from Stony Brook University suggested that while some areas are overharvested and other fishing grounds are being restored, because of ocean acidification it may be impossible to bring back many previous shellfish populations. While the full ecological consequences of these changes in calcification are still uncertain, it appears likely that many calcifying species will be adversely affected when exposed in experiments to pH reduced by 0.2 to 0.4. Larvae of a temperate brittle star, a relative of the common sea star, fewer than 0.1% survived more than 8 days. There is also a suggestion that a decline in the coccolithophores may have secondary effects on climate, contributing to global warming by decreasing the Earth's albedo via their effects on oceanic cloud cover. All marine ecosystems on Earth will be exposed to changes in acidification and several other ocean biogeochemical changes. The fluid in the internal compartments where corals grow their exoskeleton is also extremely very important for calcification growth. When the saturation rate of aragonite in the external seawater is at ambient levels, the corals will grow their aragonite crystals rapidly in their internal compartments, hence their exoskeleton grows rapidly. If the level of aragonite in the external seawater is lower than the ambient level, the corals have to work harder to maintain the right balance in the internal compartment. When that happens, the process of growing the crystal slows down, and this slows down the rate of how much their exoskeleton is growing. Depending on how much aragonite is in the surrounding water, the corals may even stop growing because the levels of aragonite are too low to pump into the internal compartment. They could even dissolve faster than they can make the crystals to the skeleton, depending on the aragonite levels in the surrounding water. Ocean acidification may force some organisms to reallocate resources away from productive endpoints such as growth in order to maintain calcification. In some places, carbon dioxide bubbles out from the seafloor, locally changing the pH and other aspects of the chemistry of the seawater. Studies of these carbon dioxide seeps have documented a variety of responses by different organisms. Coral reef communities located near carbon dioxide seeps are of particular interest because of the sensitivity of some coral species to acidification. In Papua New Guinea, declining pH caused by carbon dioxide seeps is associated with declines in coral species diversity. However, in Palau, carbon dioxide seeps are not associated with reduced species diversity of corals, although bioerosion of coral skeletons is much higher at low pH sites. Other biological impacts. Aside from the slowing and/or reversing of calcification, organisms may suffer other adverse effects, either indirectly through negative impacts on food resources or directly as reproductive or physiological effects. For example, the elevated oceanic levels of CO2 may produce CO2-induced acidification of body fluids, known as hypercapnia. Also, increasing ocean acidity is believed to have a range of direct consequences. For example, increasing acidity has been observed to reduce metabolic rates in jumbo squid, depress the immune responses of blue mussels, and make it harder for juvenile clownfish to tell apart the smells of non-predators and predators, or hear the sounds of the predators. This is possibly because ocean acidification may alter the acoustic properties of seawater, allowing sound to propagate further, and increasing ocean noise. Calcium carbonate ions are very important when it comes to building organisms, as they use calcium to build skeletons and shells. OA affects ocean species to a varying degree. Many plants do well with high CO2 levels, but organisms that calcify like clams, mussels, corals and sea urchins might not do so well because everything in the ocean is connected, including the food web. Since OA is such a large event because the ocean takes up 71% of the Earth's surface, OA is being referred to as climate change because it will affect the whole planet if the ocean becomes acidic. This impacts all animals that use sound for echolocation or communication. Atlantic longfin squid eggs took longer to hatch in acidified water, and the squid's statolith was smaller and malformed in animals placed in seawater with a lower pH. The lower pH was simulated with 20 to 30 times the normal amount of CO2. However, as with calcification, as yet there is not a full understanding of these processes in marine organisms or ecosystems. Another possible effect would be an increase in red tide events, which could contribute to the accumulation of toxins in small organisms such as anchovies and shellfish, in turn increasing occurrences of amnesic shellfish poisoning, neurotoxic shellfish poisoning and paralytic shellfish poisoning. Non-biological impacts. effects. Leaving aside direct biological effects, it is expected that ocean acidification in the future will lead to a significant decrease in the burial of carbonate sediments for several centuries, and even the dissolution of existing carbonate sediments. This will cause an elevation of ocean alkalinity, leading to the enhancement of the ocean as a reservoir for CO2, with implications for climate change as more CO2 leaves the atmosphere for the ocean. Impact on human industry. The threat of acidification includes a decline in commercial fisheries and in the Arctic tourism industry and economy. Commercial fisheries are threatened because acidification harms calcifying organisms which form the base of the Arctic food webs. Pteropods and brittle stars both form the base of the Arctic food webs and are both seriously damaged from acidification. Pteropods' shells dissolve with increasing acidification, and the brittle stars lose muscle mass when regrowing appendages. For pteropods to create shells, they require aragonite, which is produced through carbonate ions and dissolved calcium. Pteropods are severely affected because increasing acidification levels have steadily decreased the amount of water supersaturated with carbonate, which is needed for aragonite creation. Arctic waters are changing so rapidly that they will become undersaturated with aragonite as early as 2016. Additionally, the brittle star's eggs die within a few days when exposed to expected conditions resulting from Arctic acidification. Acidification threatens to destroy Arctic food webs from the base up. Arctic food webs are considered simple, meaning there are few steps in the food chain from small organisms to larger predators. For example, pteropods are a key prey item of a number of higher predators, larger plankton, fish, seabirds, whales. Both pteropods and sea stars serve as a substantial food source, and the removal from the simple food web would pose a serious threat to the whole ecosystem. The effects on the calcifying organisms at the base of the food webs could potentially destroy fisheries. The value of fish caught from U.S. commercial fisheries in 2007 was valued at $3.8 billion, and of that 73% was derived from calcifiers and their direct predators. Other organisms are directly harmed as a result of acidification. For example, decrease in the growth of marine calcifiers such as the American lobster, ocean quahog, and scallops means there is less shellfish meat available for sale and consumption. Red king crab fisheries are also at of serious threat because crabs are calcifiers and rely on carbonate ions for shell development. Baby red king crab, when exposed to increased acidification levels, experienced 100% mortality after 95 days. In 2006, red king crab accounted for 23% of the total guideline harvest levels, and a serious decline in red crab population would threaten the crab harvesting industry. Several ocean goods and services are likely to be undermined by future ocean acidification, potentially affecting the livelihoods of some 400 to 800 million people depending upon the emission scenario. Impact on indigenous peoples. Acidification could damage the Arctic tourism economy and affect the way of life of indigenous peoples. A major pillar of Arctic tourism is the sport fishing and hunting industry. The sport fishing industry is threatened by collapsing food webs which provide food for the prized fish. A decline in tourism lowers revenue input in the area and threatens the economies that are increasingly dependent on tourism. Acidification is not merely a threat but has significantly declined whole fish populations. For example, in Scandinavia, studies conducted on acidic water revealed that 15% of species populations had disappeared and that many more populations were limited in numbers or declining. The rapid decrease or disappearance of marine life could also affect the diet of indigenous peoples. Possible responses. Reducing CO2 emissions. Members of the Inter-Academy panel recommended that by 2050, global anthropogenic CO2 emissions be reduced less than 50% of the 1990 level. The 2009 statement also called on world leaders to acknowledge that ocean acidification is a direct and real consequence of increasing atmospheric CO2 concentrations, is already having an effect at current concentrations, and is likely to cause grave harm to important marine ecosystems as CO2 concentrations reach 450 and above. Recognize that reducing the buildup of CO2 in the atmosphere is the only practicable solution to mitigating ocean acidification. Reinvigorate action to reduce stressors such as overfishing and pollution on marine ecosystems to increase resilience to ocean acidification. Stabilizing atmospheric CO2 concentrations at 450 ppm would require near-term emissions reductions, with steeper reductions over time. The German Advisory Council on Global Change stated, in order to prevent disruption of the calcification of marine organisms and the resulting risk of fundamentally altering marine food webs, the following guardrail should be obeyed. The pH of near-surface waters should not drop more than 0.2 units below the pre-industrial average value in any larger ocean region. One policy target related to ocean acidity is the magnitude of future global warming. Parties to the United Nations Framework Convention on Climate Change adopted a target of limiting warming to below 2 degrees Celsius, relative to the pre-industrial level. Meeting this target would require substantial reductions in anthropogenic CO2 emissions. Limiting global warming to below 2 degrees Celsius would imply a reduction in surface ocean pH of 0.16 from pre-industrial levels. This would represent a substantial decline in surface ocean pH. Climate engineering. Climate engineering has been proposed as a possible response to ocean acidification. The IEP statement cautioned against climate engineering as a policy response. Mitigation approaches such as adding chemicals to counter the effects of acidification are likely to be expensive, only partly effective and only at a very local scale, and may pose additional unanticipated risks to the marine environment. There has been very little research on the feasibility and impacts of these approaches. Substantial research is needed before these techniques could be applied. Reports by the WGBU, the UK's Royal Society, and the US National Research Council warned of the potential risks and difficulties associated with climate engineering. Iron fertilization. Iron fertilization of the ocean could stimulate photosynthesis in phytoplankton. The phytoplankton would convert the ocean's dissolved carbon dioxide into carbohydrate and oxygen gas, some of which would sink into the deeper ocean before oxidizing. More than a dozen open-sea experiments confirmed that adding iron to the ocean increases photosynthesis in phytoplankton by up to 30 times. While this approach has been proposed as a potential solution to the ocean acidification problem, mitigation of surface ocean acidification might increase acidification in the less inhabited deep ocean. A report by the UK's Royal Society reviewed the approach for effectiveness, affordability, timeliness and safety. The rating for affordability was medium, or not expected to be very cost-effective. For the other three criteria, the ratings ranged from low to very low. For example, in regards to safety, the report found a potential for undesirable ecological side effects, and that ocean fertilization may increase anoxic regions of ocean. Carbon-negative fuels. Carbonic acid can be extracted from seawater seawater as carbon dioxide for use in making synthetic fuel. If the resulting flue exhaust gas was subject to carbon capture, then the process would be carbon negative over time, resulting in permanent extraction of inorganic carbon from seawater and the atmosphere with which seawater is in equilibrium. Based on the energy requirements, this process was estimated to cost about $50 per ton of CO2. Gallery.